Okay, let's start. Uh, let's continue what we have seen in the last class. So what we have seen in the last class, okay, it is a lecture number. What is the lecture number? I think lecture number 10, right? 9 or 10? It's a 10. Modeling of combinational circuits. So what is the logic that we have seen in the last class? Off adder, right? So modeling of order, off adder we have seen. Okay, what modeling style that we have seen? We have seen the behavioral model, right? Very good. So so what is the behavioral model? What do you mean by behavioral modeling? Hmm. So if you want to describe the hardware, we have to use the input-output behavior, right? If you're using the input-output behavior based on input, output, behavior of hardware, we are able to describe. We are able to use behavioral modeling when we have input-output behavior of the hardware. Okay. If you know the input-output behavior with respect to the hardware-related input-output behavior, then only we are able to write the behavioral model, right? That is a prerequisite. So what type of statements we have used? What type of statement we have used? We have to use the procedural statements, right? Procedural statements. So what one procedural statement we use? Huh? It is called if statement we have used. Okay. We have used if statement. Okay. So like this, we have a different procedural statements are available. Okay. We can use one of the procedural statement. Right. What is the one what is the one thing that must be followed when we are using the behavioral model? What is the one thing that we have to remember when we are writing the behavioral model? Or I can say the two things that we have to remember. What are the two things that we have to remember? Okay. So the first thing is output must be declared as what? Register data, reg data type, right? Is that point is clear? What is another thing? We have to use always block. We have to use always block. So these are the things that we have seen in the last class about writing the behavioral model. Okay. Input output behavior, we should know. We have to write the output as a register data type, and always block we have to use. Within the always block, we have to write the procedural statements. Okay. Right. So people are not happy with the behavioral modeling for some reason. Okay. Sometimes so because if you want to write the input output behavior, it's a long thing actually. Okay. Then definitely we are not interested. Verilog has given another provision. We can take another modeling style. That is called data flow model. Okay. Of course, behavioral modeling is a very important because everybody write Verilog code in the behavioral modeling only. But we will see why it is so. Okay. So now look at another important modeling style is data flow model. Data flow modeling. Okay. Now, if for example, if I take this is my hop header, for example. Okay. Let me copy this particular statement. Okay. For example, this is my hop header. Copy. I want to paste it here. Okay. So I want to see is there any change in the external view if you're changing the data flow modeling? If you are changed from behavioral model to the data flow modeling, is there any change in the external view? No change, right? Okay, fine. That's what the first thing that you should observe. The next point is what is required for this one? What is the prerequisite for the data flow modeling? We should have mathematical equations, right? Okay. So where this mathematical equation came from? These are from truth table. Okay. Apply by using the truth table, we'll get by using the Boolean algebra, we are able to get this particular thing, right? Fine. Now, this is what the prerequisite to write the data flow model. That means this is also simply input-output behavior we are representing, but in the form of equations. It is also input-output behavior only, but it's in the form of equations. Okay. So let us take the program and what need to change in the given program. Okay. Let me go and take this program. Okay. Okay. So what modification that you can write here? Is there any external things are changing here? No change, right? Input A and B is the same. And what about the output? You should not write register data type when you are writing the data flow model. Okay, the register data type is exclusively for behavioral model. We should not write any other thing. Okay. Now, do we need to use the always block? Always block is not required, right? Okay, so therefore, definitely we don't need any kind of always block because always block is meant for representing the internal view, which is in the input output behavior, just like a truth table nature, right? We don't need any kind of this information. Okay, this much information is not needed. Okay, but it seems that for a small block, for a small half header, if you're writing this much code, you feel that behavioral modeling is not a suitable one. Okay, but when we behavioral models will deal effectively when we are taking the complex programs, complex designs. It's a very easy writing the program in the behavioral modeling. If you're talking about if you go for complex designs, okay. So, but you feel that this is a very simplest one, okay. But what we have to do, we have to write what we have to write equations. We need to write here. How do I write the equations? How can I write the equations, Boolean equations into the Verilog program? By using assignment statement. Very good. Okay, you write one assignment keyword, assign. What is the sum here? Sum is equal to, or assign equal to stands for assignment. What we are assigning? Evaluate these two things, right? A XOR B, we have to evaluate and assign, and the result is assigned to the sum. Okay, that means you have to evaluate this. The evaluated result will be assigned to sum. So that's what the equality operator says. Okay, but the question is that plus overall the symbol, that is actually a Boolean algebra operator. It is a Boolean algebra operator. But what operator we have to use here? We have to use here Verilog operator. Okay, what is the Verilog operator here? It is actually a cap. Okay, so let me write here, for example, if it is an AND gate, for example, you have to use, this is the operator. If it is an OR gate, for example, you have to use this one. If it is a NOT gate, for example, you have to use NOT something like this. If it is XOR, for example, then you have to use cap. If it is NAND, for example, we have no separate operators available. Just you have to use not and that I have to write. Okay. If it is a NOR, we have no separate operator, not OR. If it is an XNOR, for example, again here also not of XOR. So these are the Verilog operators we have to use in order to write a Verilog program in Dataflow model. Okay. Similarly, we have to write another assignment statement because of two equations that are there. Okay. Now simply assign and C out is equal to what operator I have to use? Ampersand, A and B. And is not required, right? Any question? Okay. Okay. So what is your conclusion depending upon the behavioral modeling and the data flow model? Can you write the behavioral model here, the behavioral model and the data flow model? Okay. So here, what type of statements I have used here in the behavioral model? Procedural statements. Procedural. What statements I've used here? Assignment statements. I'm using the assignment statements. Okay, that is the first thing. And the second point is which one you feel more comfortable in terms of the length of the code. Data flow modeling is you feel that it's a very good, but actually if the complexity of the circuit or the size of the circuit is very, very small, then better you have to go for data flow model. If the complexity of the circuit is more and more, then it's very easy to write in the behavioral model. Okay, we'll see in the later when we talk about the sequential circuits. Okay, we find a very big advantage by using the behavioral model than that of the data flow model. Okay, so therefore, it seems that it's better for complex circuits, for easy circuits. Okay, that's what the difference you have to remember. Now we have gone for one level below, right? We have gone for one level below. That means we started with the truth table, and then you feel that it's not that much great to write for a smaller circuit in the behavioral model because the length of the code is more. That's the reason why you have gone for the one step level, one step below. That means data flow model. The third approach is, okay, you are not also not comfortable to write in the data flow model. Instead, I can go for another approach that is called gate level model. Okay, once you have equations in your hand, you can write the gate level circuit, right? That means there's a simple structure, you are able to do it. Okay, so you're able to do it. Next, we'll go for gate level model. Gate level model. Okay, that means we can go one step below also. That is called from the equations to the circuit. Okay, so what is the logic diagram for this? What is the internal circuit for this one now? For example, this is actually, we have seen that, of course, it is already written, right? Okay, let me take a copy and paste that. Let me take, this is a hop adder, copy, and I want to paste here, right? So now the internals, what is the internal circuit of the hop adder? I know that there is a one exclusive OR gate is required, one AND gate is required. This is for, this output is for the sum, this output is for C out. So carry. Let me consider this as a carry. So therefore here you can see that A is connected here, B is connected here, right? A, B. Okay, this is what inside of the block. How I have derived this gate level circuit? From the mathematical equation. It's not a straightforward one. Okay, that means so if you want to get this circuit, first you have to have a Boolean equations. Okay, unless otherwise if you don't have any Boolean equations, we are not able to draw this particular, right? Okay, that means two steps. Starting from the truth table, we have gone to this one by 2 levels. Okay, but how to write the program for this one? So let me take this program again. Okay, so is there any change in the external view now here again? No change. External view is the same, but internal view is changed. Okay, so let me change this the name of the software also. Okay, since it is a behavioral gate level model, I'm going to write here is just I'm adding a GM, just my identification purpose. Okay, and what about these particular equations? We should not use these equations, right? We should not use this equation because internal is different actually. Okay, what is the internal circuitry? It is, as we can see here. What type of statement we have to use? Here we have to use the gate primitive statements. What statement we have to use? Gate primitive statements. Okay, there is some meaning for the primitive statements. So we'll talk about this one. Just give me some time. Okay, therefore I have an exclusive OR gate here, right? Let me call this is the G1 gate. This is the gate name is G2 gate, for example. Okay, so I have to take the XOR is one my gate, XOR. So XOR stands for, the keyword is XOR. XOR. Okay, what is the name of this gate? G1. It is an optional actually. G1 is an optional. If you write, it's okay. If not write, it doesn't matter. But when you are synthesizing the circuit, it's very, very important. Okay, therefore, better to habituate to write the, when you're writing any component, you write the name of that particular component within the program, right? Okay. So since it is a gate primitive, first we have to write the output first. Okay, then you have to write the inputs. The primitive stands for, the definition of this hop adder is available in the library. Okay, therefore we are using the Xilinx software, right? In the Xilinx software, what you can see, there are the different libraries that are available. In that library, this kind of exclusive OR gate is available. Okay, we are making use of that exclusive OR gate. So therefore, how they have defined the exclusive OR gate? They have defined the exclusive OR gate, the first output they have mentioned, and then they have defined the input and outputs. Okay, sorry, inputs they have mentioned. So what is the output for this one? The output for this one is sum. What are the inputs for this one? A and B. Right? Okay. Next, what about another gate available? And okay, since it is a keyword, I'm writing another color. And this is called G2. This is a carry, and A comma B. Okay, right? So this is how we have to write. We have to model. This is how we have to model any hardware by using the Verilog HDL. Essentially, we have 3 ways that are there. One is called behavioral model. Another one is called Dataflow model. The third one is called GateLevel model. Okay. So later we are going to talk about the structural model. Okay. Later we are going to talk about a mixed model. Okay. Uh, let us take a mixed model. For example, it is possible that we can mix any two modeling styles. Okay. Any two models or three models we can combine together and we'll get that one. So that point we will see later, a little bit later, but it's too early to understand that one. Okay. If I give any hardware, any combination circuit, if I give, then you're in a position to describe any modeling style. Not necessary that one particular circuit is described only in particular modeling style. It's not true. Okay. You can write any modeling style according to the specifications they have given. Right. Now the question is that, yes, somehow we are able to describe this one, how the circuit is look like. But now the question is how to verify this one. How to verify this one. So what is the verification of this logic function? Writing the test bed, right? So that means, so what is the necessary inputs A and B so that this block will be evaluated and give you as an output. Okay. So I will tell you some steps we have to follow so that we are able to write the test bench for it. Okay. So let's write the test bench now. Okay. For example, this is your half adder. This is your half adder design under test. Okay. That means this is what you design under test means this is what you are going to test. Okay. That means it will produce sum. This will produce carry. Okay. Now, what do you mean by testing of this one? Apply the input A and B. How you are giving the input here? How you are giving the input here? First, you give at t is equal to 0 time. T is equal to 0 nanoseconds, for example. You give A is 0, B is 0. Right? After some time, that means, for example, t is equal to 1 nanosecond, for example. You change A is keep it same and B is also 1. B is 1. Right? And at some other time, t is equal to 2, for example, you apply, here is the 1, here is the 0. And t is equal to, for example, 3 nanoseconds, you apply both are 1 and 1. These are the usual combinations we can apply so that we can verify the sum and carry, right? Am I right or not? Now, this is what important actually. Of course, you know very well that what are the different input combinations I have to apply. Fine, good, keep it like this. And if you want to test this one, we are going to use, that means whatever the information that you're giving here, okay? But this is also, we have to give in the form of code. We have to give this is also in the form of code. Okay? That means we have to use the Verilog constructs to create or to develop this particular information. Okay? Let's see how we are applying. Before going to this one, since we are testing this half adder, we need to have a test bench to cover this half adder. Okay, that means this is the test bench actually. So what is the responsibility of the test bench? If I ask this question, what is the responsibility of this test bench? Provide the necessary input for the half adder A and B. Okay, that means it has to give the input for this one. For example, it will give you input is connected here, and this is also connected here. Okay, let me take this is A, and this is a B. Are you getting this point? The test bench will provide you input A to half adder. Test bench also will provide another input that is called output. Okay. So if I say that which one is a subcomponent, test bench is a subcomponent to the half adder, a half adder is a subcomponent to the test bench. According to this particular representation, which one is the lower and which one is the bigger one? Which one is the top, which one is the bottom one? Test bench is a top one, and design under test is a subcomponent to it. Okay. Therefore, when we talk about the test bench, you always treat the test bench as a top module, and this is a component, subcomponent. Are you getting the point? Always remember that design under test is a subcomponent to the test module. Okay. Okay. So that's point you have to remember. Just essence of this test bench is provide the necessary input signal to the design under test. Nothing else here. Right. So as I mentioned that the test bench is also a module. Okay. Let us go and talk about the module. Okay. How can we start writing the program here? Module. Okay. Let me write what is the name of this module. For example, this is what the recommended approach. Okay. Half adder underscore test. Half adder underscore test. That is the name of the test bench. And don't write any variables information here. You did not write any variables at this place. Okay. And we have to end this module, right? Somewhere you can write the end module. Okay. Now the question is, you are using some variables. Okay. Okay. And look at this one. This is called, for example, the test bench is producing two variables are required. See, for the half adder requires two variables, A and B. Okay. That variables are generated whom? Test bench is generating the two variables. Okay. Let me call test variable A and test variable B. Okay. That means, for example, half adder, for example, a design under test having the 10 variables, for example, then the test bench should have 10 variables. Should have 10 variables. Okay. Therefore, and one more point also look at this one. So the output of this one is also connected to the test bench. The output is also will be connected to the test bench. Okay. That means you apply the input to the test bench. Sorry, apply the input to the half adder, process it, and take the output by the test bench. Okay. Therefore, let me write here one important point. The responsibility of the test bench. Okay. Test bench will generate the input values. That's what we have tried. Input values, and also shows the results as well. Results as well. Okay. See, applying the input is not only his point. Okay. Once you apply the input signals to it, input values to it, the design will be processed, evaluated, and the result must be shown by the test bench only. Okay, the two responsibilities, applying the inputs as well as showing the output, is also two things that we have to remember. Okay, so therefore, this is what the primary advantage of using the test bench. Okay. Right. Now, what are the variables you are using here now? Again, here also, I'm not going to write these things here. Let me write his sum, and this is called carry. For the test bench point of view, this is called two variables I'm using, T sum and T carry. Did you find the difference between the sum and T sum and carry T sum? Okay, right. So what variables that you are using in the test bench? So you're using the test bench variables are TA, comma, TB. Okay. You have to remember that this is a registered data type. Please remember that this is a registered data type. Why it is a registered data type? Because we have to set this for A value and B values, we have to keep somewhere. Okay, all the possible combinations I want to keep somewhere. That means it must store the values of A and B. That's the reason why TA and TB are the registered data type. Okay. Now, what about the output? The output variables are T sum, comma, T carry. These are the output variables. Okay. But these must be wide data type. It must be wide. The moment whatever the stored value 00 you have given, evaluated, and instantly that will give you. Okay. You need not store that output. You need not store the output. Whereas if you apply 01, for example, that means the next state we have stored somewhere, that is 01. Apply it to that one, and you will see the output. And you need not store that output. If you're not able to store the output, definitely you can write that variable data type should be wide data type. Okay, right. This is the second step that we have to follow. Right? Next. What is the next point that we have to remember? What is the test information that we would like to put? We would like to give what kind of test information? What is the test information? Test information will be given in the form of initial block. By using the initial block, begin and end, we would like to write the initial information. Sorry, we would like to give you the what is the A and what is the B. Okay, what is A here? What is the first A? A is equal to 0 and B is equal to 0 at T is equal to 0 nanoseconds of time. Okay, after 1 nanosecond, I want to change input pattern 00 to 01. What I have to write then? So we have to add the delay here by using the hash symbol. Hash 1, what I can write? A is equal to 0 and B is equal to 1. This is the second case I have given. What is the third case? At 2 nanoseconds. That means we have to add 1 nanoseconds to the previous value. We have to add 1 nanoseconds to the previous value. It becomes the 2 nanoseconds now. Then what is this value? At 2 nanoseconds, what you can apply? A is equal to 1, B is equal to 0. At another 1 nanosecond, for example, then A is equal to 1 and B is equal to 1. Okay. Of course, I'm so sorry. What variables we have used here? Can you please let me know? Not A, TA, TB, TA, TBs. Did you catch this point? These are the variables I'm using inside of this test bench. TA and TB, and two variables are required. Two variables are TA and TB. Two output variables are required, T sum and T say. So I have to describe everything in this test bench with the help of the given declared variables, right? Declared variables. Now I have to apply these input values on the half adder. Am I right now? So what is the half adder? How can I call half adder? I can call half adder directly something like this. For example, I want to verify this one. I want to verify this particular module. That means I have to take as it is the name we have to write. Okay. I'm applying these inputs on this one. Okay. Let me write what is this name of this module. It's very, very important. You have to write the name of this module because it is a component to the test bench. That's what I'm talking about this one. So what is this one here? This half adder is a component to the test bench. That's the reason why we have to give the name of this one. Okay. So we have to give the name of this one as M0. Anyone in the class, what is the modification that I have to write for the TA, TB, sum and carry? What you have to write? So what here I have to write, what here I have to write, what here I have to write? TA, TB. Okay, very good. So let me write here is TA, TB, T sum, and T carry. Very good. That is the thing. So when you would like to stop the simulation, okay, these values will be applied on this one and it will produce some kind of output. Okay. And where should I stop my simulation? Where should I stop my simulation? Okay, for this one also, we have to use the recent one. We have to think about, we have to use the initial block only. Initial dollar at 5 nanoseconds, sorry, hash 5 nanoseconds dollar stop. Okay, this is the system task we have to use to stop the simulation. Okay, this is the to stop the simulation. That means after 4 nanoseconds, after 3 nanoseconds, you don't need any kind of simulation. Okay, you stop the simulation at exactly at 4 nanoseconds is enough. 4 nanoseconds, stopping the simulation at 4 nanoseconds is the best choice instead of 5 nanoseconds actually. Okay, so these are the things. This is a very simple and straightforward right in the test bench for any model. For example, if I want to test a behavioral model, what modification I have to do it here? Instead of data flow model, I have to call behavioral model, right? So since you have three modeling styles, you need not write three test benches. Only one test bench is sufficient to test it. Okay. So therefore, these are the essential components. Okay. Today we stop here. Okay, and tomorrow we will see what is the some kind of modifications on the test bench so that we will have a better way of writing the test bench. It's a very simple and straightforward and very easy way to write the test bench, but we have to change something for the better way of writing the test. Okay, we stop here today. We'll see you in the next one.